Okay, so let's go back. All right, well, thank you very much. It's really a pleasure to be here. Let me add my words of congratulations to Andy. I've long been a fan of his work. I don't think I could do any of it. We do something that is very different. And let me see if I can get rid of this guy. Huh. All right, I guess I can't, so you'll just have to look at it. What I want to talk about today is really something that's been a 20-year quest over, off and on over the years in my group, and something that I've been really fascinated by for much longer than that, since actually I was a graduate student at the University of North Carolina. And that is the technique that, with a tip of the hat to Prince, I am hereby dubbing, formally known as immersion. And I will explain that to you as we go through the talk. So what is immersion? Okay, why can't I get this? Well, many of you know that we've been interested over the years in understanding the molecular structure and more recently dynamics of interfaces between solids and liquids. And in particular, the questions that we kind of like to know are things about the molecular details and the processes and chemistry that influences those. So back in the mid-1970s, there was a technique that was introduced by a physicist, actually, by the name of Wilfred Hansen, that he called immersion. And for those of you that don't know what immersion is, it's the act of emerging. That comes right from the dictionary. And because there had been some confusion about this over time in the literature. And in terms of the embodiment of the method, basically what this is you take your solid substrate, immerse it into some kind of a fluid, and then remove it, leaving yourself with an immersed layer, a thin fluid film on the surface that you could ostensibly probe, which contained the interfacial information with no interference from the bulk solution. And that was, in fact, the nature of my fascination with this technique at the outset, because we wanted to do spectroscopy on it. And in fact, we have done lots of spectroscopy on it. The thing about this, though, is that we could never rationalize the thicknesses of these immersed layers that we were seeing. And after a while, everybody was like, well, it really doesn't matter, but it really mattered to me. And I just got mad and decided that we were going to figure this out. And this is also an interesting scientific story, because this is an area where actually the theory lagged a little bit behind, the critical theory lagged a little bit behind the experiments, and I'll tell you that story today. Now, when Hansen introduced this, for electrochemical interfaces in particular, as shown here, of course, what you have across the electrochemical interface is a strong potential gradient that presumably would help provide electrostatic attraction between the fluid layers and the electrode surface, and of course those would drag along with them their solvent molecules. And Hansen repeatedly stated in his papers that the shear plane then where the electrolyte would become unzipped would be somewhere outside of the outer Helmholtz layer. Okay? And so that was the view that we had going into this work. And in fact, he had some nice evidence for this in the early days of immersion. He showed electroreflectance spectroscopy, where the in situ matched very closely to those in the immersed films. He made vibrating Kelvin probe work function measurements that showed a linear change in work function with potential at which the immersion was done, all of which suggests that the ionic content of the interface was clearly retained, but he never was able to make any measurements that showed whether or not the solvent was present. And in fact, of the measurements that he did do, he came to the conclusion that there was never any solvent around. And in the early 90s, when we got back to this, we proved that that was not correct. But then understanding what did come out and why it came out is what has really kind of captured my attention for the last almost 2 decades. Now, we were really motivated by our early work in this area by one experiment that he did publish in the late 1980s, in which he attempted to couple infrared reflectance absorbance spectroscopy to immersion in this kind of a configuration with a rotating electrode that would rotate through the fluid that he would then post-probe with an infrared beam, or in fact any optical beam. And these are some of the spectra. The first system he looked at, and in fact the only system that he looked at that's in the literature, was for an adsorbed layer of the dye crystal violet that adsorbs onto gold electrodes. And you can see that the spectra do indeed change as a function of electrode potential. You see that there's a huge amount of interference from water vapor that you sample in this transmission measurement, basically through the gas phase above the liquid, which actually turns out to be very important in terms of stabilizing the immersed layer. But all of these vibrational bands that you see are due to the crystal violet, and he never definitively saw any evidence for solvent. Now, in fact, we later came back, and the first stuff that we did in this area was to prove that you could in fact see solvent. We've done lots of studies looking at solvent in various environments. We took his design, which really was brilliant in my estimation, and we changed it a little bit in the following way. We brought, instead of having a big reservoir of fluid, we just had a very small droplet of fluid that we brought through a capillary against a rotating surface. In most of our experiments, we chose silver just because it's convenient optically. We did it in a design that is shown up here. The salient point is we reduced the gap that was sampled by the infrared beam, or in this particular case, to a very small thickness so that you weren't overwhelmed by the solvent vapor. But essentially, it was the same experiment as Hansen tried to do in the late 1980s. Now, this turned out to be really a ripe area for exploration. We've got lots of data, some beautiful spectroscopic data on solvent, and I'll show you a few at the end. But really what I want to talk about today is the quest that we had to undertake in order to understand the thickness of these layers that came out, because they didn't seem to make any sense, and I'll explain to you why that is. Now, as I said, Hansen had published in many papers that the shear plane was at the outer Helmholtz, was just outside the outer Helmholtz plane. And it took us a while to understand why that might be. And so at the outset of our work, the questions that were kind of on the table were, how thick is the immersed layer? Is there solvent immersed? Because up to that point, he had never showed that there was any solvent that was in any of his measurements. How does the thickness of the immersed layer depend on potential, and how does it depend on ionic strength? Well, answering the first two questions were more or less easy. These are not easy experiments because you're looking at very thin films, but in terms of actually getting data to answer these, we did it relatively straightforwardly. The things that were much more difficult to answer and then explain were the questions 3 and 4 about how the thickness depends on potential and ionic strength. And so you start with this with some naive expectations and predictions, and you start for electrochemical interfaces with a simple Gooey-Chapman-Stern model, which obviously suggests that the double layer becomes more compact as the potential increases or the ionic strength increases, and you predict that these immersed layers should either slightly contract with increasing surface charge, in other words, increasing surface potential, and/or that you would expect some kind of a smooth systematic change with change in potential. So at that point then, I had a student who undertook really an excruciating series of measurements to try and validate these predictions. And these are the data we chose to study electrochemists' favorite aqueous electrolyte, sodium fluoride. over a range of concentrations and measure using ellipsometry the immersed layer thicknesses. We now call them residual films. And these are what you see for residual film thickness as a function of concentration. And these, let me make a couple of points. First of all, we're talking about film thicknesses that are unbelievably thin, right? Nanometers or less. And that's why the error bars are apparently so large, but each of these points is on the basis of literally 20 or 30 different surfaces, different measurements, so they're real. And what you see is completely, at least for us, completely unexpected. You see essentially a step function change in immersed layer thickness with concentration. And the other thing that you see, and I'll just summarize this in terms of the two key observations, there is essentially no dependence of thickness on surface charge. Each of these data points is at a different electrode potential, at potentials both positive of and negative of the potential of zero charge. And so there's essentially no dependence on electrode potential. And there is an unexpected step function change in thickness with electrolyte concentration. Okay? So at that point, we had some very unexplained results, and we set about what turned out to be a multi-year quest through all kinds of different types of literature to understand this. So the interesting thing is then you develop these pictures of the electrochemical interface in the concentration regime of low concentrations and high concentrations. And for the low concentrations, the so-called shear plane, if that's what it is, where the electrolyte unzips, is actually about half a nanometer, 5 angstroms. It's thinner than the outer Helmholtz plane. And for the high concentration systems, it's about 1.5 to 1.7 nanometers in thickness. It's thicker in all cases than where the outer Helmholtz plane is. But what's a few angstroms among friends? It was more or less at the outer Helmholtz plane, but there was no systematic dependencies as was expected, and we couldn't rationalize what was changing about these films. So then you begin to ask yourself, okay, so what should be in the interface that is immersed? And at low concentrations, again using classical Guichev and Stern models, you can calculate the composition of the interface in terms of concentration of different ions as a function of distance from the electrode, and you come to the conclusions for both low concentrations and high concentrations of electrolytes that for residual films of the low concentration, it should consist mainly of fluoride ions. And these calculations were done for immersion on a positively charged electrode. Whereas at high concentrations of electrolyte, you should have not only fluoride ions, but also sodium ions in this thicker film that actually comes out of solution. And so we set about then proving that that's what we did or did not have, and again, more surprises. We did XPS on these immersed electrochemical interfaces, and after this is actually something that was tried back in the 80s, and it was always somewhat questionable about what was being observed. The interesting thing about these measurements is that there was absolutely no evidence for any significant amount of fluoride in these interfaces. Okay, whereas for both concentrations, that should be one of the predominant ionic species. And the second thing that was somewhat surprising is that there was a surprising amount of oxygen observed in the interfaces. And it turns out that actually these similar studies had been done by Doppelhofer and his colleagues in Germany around the turn of the century, and our findings are completely consistent with what they had also reported. And if you look carefully at the XPS data, what you see is that there's actually two chemical environments for the oxygen 1s, one of which comes from adsorbed hydroxide ions at the interface, and one of which actually comes from water. Okay? And the ratios do change as you change the electrolyte concentration of these two amounts. And so there's no fluoride, but the adsorbed counterion in this case at these positively charged electrodes is actually adsorbed hydroxide. And this is the first evidence that there is really water at these interfaces. And then you also see two chemical environments for sodium, which is somewhat surprising. One that is due to sodium that's electrostatically bound to the adsorbed hydroxide, and then sodium that is just carried along as predicted in the immersed layer that is hydrated. Okay? So it surprises somewhat about the composition of the immersed layer. Now, the interesting thing is you take all this XPS data, you take what you know about the electrode surface charge, and you calculate what the surface concentration, or the equivalent surface concentration, because actually it's in a small volume, of these different species is with electrolyte concentration. And you see that it systematically changes both for the hydroxide and for the sodium. And that's the point. It systematically changes with concentration, as you might expect. There is no step function change in ionic composition in the interface. Okay, so this does not, in and of itself, explain the step function change that we see in the thicknesses of these residual layers. So again, we're back to the drawing board. And trying to understand if this doesn't explain why we see this change, the step function change in thickness, what does? And we went back and we asked ourselves, what was Hansen thinking about when he made the statement that the electrolyte should come unzipped somewhere around the outer Helmholtz plane? And we came to the conclusion that this is a decidedly hydrodynamic viewpoint of what should be happening at a charged interface that was probably based on what is believed to be the case in the colloid community about where the fluid moves past the colloids as it floats around in solution. Okay? So we had a new handle to go investigate, that being hydrodynamics. And so we dove into the the fluid dynamics literature, and went back to the literature to find an old paper and actually several modifications of it since then, but work done by Landau-Levick back in the 1940s about the thickness of layers that were pulled out onto a solid surface of a moving plate. And this is an equation that, in its modified form, comes from this original work, and it defines the thickness of this residual layer, H, as a function of the system variables that are the fluid viscosity, the velocity, the withdrawal velocity, the density of the fluid, and its fluid vapor surface tension. Okay? And this equation has been used to predict in dip coating, successfully predict in dip coating, thicknesses of layers that are withdrawn in dip coating procedures. But in fact, if you take this equation and our system for the withdrawal velocities that we're using, typically on the order of several hundred microns per second, this relationship predicts that the thickness that we should be withdrawing is on the order of 1 micron, okay? And we're measuring 1 nanometer, okay? It's a big, big difference. So clearly hydrodynamics is problematic here. And the real breakthrough came, we asked the question, well, does this relationship hold for all conditions of velocity? And that turned out to be a really important question, and was not really adequately answered until the work of an applied mathematician by the name of Jens Eggers in Great Britain answered this in the mid-2000s with a development of a relationship that allowed you to define when you were in the hydrodynamic regime and when you were not, okay? And so it turns out that the Landau-Levick equation only applies when you are above some critical value of velocity, this so-called V crit, okay? Which is related to the critical capillary number. That's what the Ca is. It's not calcium. And so, in fact, what we knew then, what we were able to answer was whether or not we were operating in a regime of hydrodynamics. And so the take-home message here is that for dewetting, as we now Again, calling it because this is the process of forced dewetting and much more descriptive than immersion. But for water on a moderately wetting surface, like silver, for example, this critical velocity is 12 centimeters per second, and we're going at hundreds of microns per second, which is well below that. Okay? So that finally gave us evidence that we were not operating in a hydrodynamic regime, and that hydrodynamics was not going to be able to explain the thicknesses that we observed. And in fact, we had other evidence, lots of other evidence in the laboratory at the time that validated that. So for example, this is really telling. We looked at a series of glycerol water solutions, looking at varying the weight percent of glycerol from 0 to 80%, right? You know glycerol, it's like honey. 80% is pretty darn viscous. In fact, it's got a viscosity of about 46 centipoise. And what we see in the forced dewetting experiment with these systems is that the residual film thickness starts out low, around a nanometer, and goes up some, but only goes up to about 5.5 nanometers, where it plateaus regardless of viscosity. Okay? Even for really, really, really viscous systems. Okay? So these data confirm the notion that hydrodynamics is not playing a significant role in this process of what we are now calling forced dewetting. So if hydrodynamics doesn't explain it, what does? Well, it turns out that if you go back into the dynamic wetting literature, go way back to the 80s, this is something that had been very much of interest to chemical engineers who were interested in dynamic wetting. And it turns out that when you go below this critical wetting velocity, which was only defined in 2004, you end up with a situation where intermolecular forces end up dominating or dictating the thicknesses of these films that you can create. And that's really the important take-home message of this, although let me elaborate this for you a little bit longer. So this is all embodied in a concept called the disjoining pressure. And basically, the disjoining pressure, capital Pi, it describes the intermolecular forces that lead to thinning of a thin film of fluid as you withdraw it from a bulk fluid solution. And so it's got three different contributions. It has a molecular contribution from van der Waals attraction between the gas phase out here and the solid phase, which serves to thin the fluid. It's got a repulsive electrostatic contribution that comes from electrostatic interactions within the film that, if they're present, serve to thicken the film. And then a structural component that is actually the least well understood of the three contributions that has to do with the extent to which there is additional structural forces in the fluid in this region that stabilizes the film. Okay? So this disjoining pressure then is reasonably well understood. As I said, it's got three contributions, the molecular that I'll say a bit more about, the electrostatic, and the structural. And in fact, DLVO theory embodies essentially the molecular, the van der Waals, and the electrostatic contributions, and allows you to separately calculate these contributions and predict what the overall total disjoining pressure of the system is. Okay? Leaving the structural component aside, which hopefully is relatively small in most systems. So, these now are well understood. The van der Waals contribution to the disjoining pressure is related to the Hammacher constant for the three-phase system. The individual Hammacher constants for each phase are calculated from their particular characteristics, and then with a combining relationship, you can get the overall three-phase system disjoining pressure, or excuse me, Hammacher constant to calculate the disjoining pressure for a given thickness, which we did. And similarly, the electrostatic contribution to the disjoining pressure is actually related to, in a charged interface, the potential at the liquid-vapor interface. We know from electrochemistry, in fact, we can measure from differential capacitance measurements the surface charge, which allows us to calculate the surface potential, and then using basically a Gooey-Chapman-Stern model, calculate what the potential is at the liquid-vapor interface to get the electrostatic contribution of the disjoining pressure. And the bottom line, and this is from my How Not to Give a Seminar slide, the bottom line is that with the thicknesses that we measure, we can calculate the different contributions, add them together to get the DLVO, and this is where the real insight came. And to make a long story short, for low concentrations, ionic strengths, the majority of the contribution to the disjoining pressure is from the van der Waals, molecular forces, intermolecular forces. The magnitudes of the electrostatic repulsive forces are comparatively very small, and so the the DLVO, sum of the two is dominated by molecular forces at low ionic strengths. At high ionic strengths, the opposite is true. The magnitudes of the electrostatic contribution to the disjoining pressure gets to be much larger. The van der Waals does not go to zero, but the overall then disjoining pressure, which is the sum of the two, is dominated by the electrostatic contributions. Okay? And so that allows us then to understand what we're seeing here in this step function change in thickness with electrolyte concentration. At the low concentrations, we're really talking about van der Waals forces leading to the creation of this residual layer on the surface as we withdraw it. As we go to higher ionic strength systems, we've got some van der Waals, but predominantly electrostatic contributions adding in. The theory predicts approximately the thicknesses that we observe. There is some difference because there are structural forces we know that we're not accounting for, but all in all, basically, when you use the theory of disjoining pressures to explain the force dewetting process, as we're now calling it, you get a very satisfying result in contrast to the hydrodynamic. So at the end of the day, we can explain these thicknesses that we see in these two different concentration regimes, which is excellent. And I will say that we've got some other data in the laboratory for other charged surfaces that actually confirms this. And so this is an interesting one. This is for silica now as a function of pH. And of course, what you do is you progressively deprotonate the surface. And the same thing happens as you go from a pH 1, where the surface is largely neutral. You see about a 6 nanometer thick film. These are thicker films now because the van der Waals attraction between the gas phase medium and the silica is much lower, and so it doesn't thin the water as much. And as you begin to deprotonate the silanols on the surface as you increase pH, you reach some point where the surface charge becomes large enough such that the electrostatic contribution to the formation of the residual layer becomes much more pronounced. pH 9, it begins to fall off a little bit. We think because actually at pH 9 we're beginning to dissolve the silica a little bit. But nonetheless, the same kind of more or less step function behavior in the residual layer thicknesses is observed, which is consistent with the model that I've shared with you earlier. So, as I said, of course, our real interest in this was to get spectroscopy information about molecular structure in these interfaces. I can't finish without showing a little bit of that, and so this is some infrared reflectance absorbance data that we got actually for these water layers at silica. And the top spectra are what the spectra in bulk look like. Excuse me, the isotropic bulk spectra look like, and then the spectra below for these three different pHs shows you the spectra in the OH region for the emersed layer, the residual films. And the take-home message is that we get, really excellent spectral data on the solvent, which really gives us a lot of insight into molecular structure of solvent in the interface. The envelope shape, if you just want to do some pattern recognition with me, you can see that the envelope shapes of the solid lines are different from those of the shapes of the bulk spectra, which tells you that the structure is indeed different. You can do all kinds of fitting to the different modes that are under this envelope and understand something about structural details, which we have done. And so those are some data for silica. Similarly, I showed you some of the thickness data for the glycerol water. This turned out to be a really interesting study because it turns out, and you can tell this on the basis of the spectroscopy, that the glycerol preferentially segregates to the interface, and these are mole fractions of glycerol for each of these three panels. The top two are essentially the bulk spectra for this condition. The bottom spectra are for the residual films. You can see that there are massive structural differences between the responses of glycerol in the interface compared to bulk solution that tell you a lot about structure, in this case a lot of structure. And so the take-home message then is that the solvent does come out, it's structurally perturbed, which is what got us into this to begin with. These films are nanometer thicknesses, which is not due to any hydrodynamic explanation, but is in fact due to intermolecular forces. And so at the end of the day, this basically summarizes what I've just said. And in hindsight, when everything's perfectly clear, you realize it's the chemistry, stupid, as we should have realized at the outset. So with that, I'd like to close and thank you for your attention. Congratulate Andy again for the Reilley Award, and thank my funding sources that funded all of this forced dewetting work, NSF and the Department of Energy, and particularly acknowledge my postdoc, Anoma Mutaligi, who has really hung in there with me on this. I'm a reasonable mathematician, but she's a lot better than I am, and so without her contributions, we would not have been able to sort through all of this theory to come to a reasonable explanation of this phenomenon. So thank you very much for your attention.
Very cool. Thank you, Jeanne. Questions for Jeanne? We have time for one or two. Over here.
I'm wondering, in terms of your disjoining pressure, for the structural component, would you think that the impact of either like highly charged protein or like a polymer layer would be an example of a structural component?
I think a better example of a structural component, I think of it in terms of just the fluid itself. And so on a surface such as silica, where we see a higher concentration of more ordered water forms, that's a contribution of structural, that's an example of a structural contribution. You're really asking about an adsorbed layer, which will certainly add thickness, but I that is a much more complicated situation. Is that a structural force? The disjoining pressure model is really developed simply for fluids, and that is an organic. Yes, I would consider it an adsorbed organic structural contribution to the layer if there were then unique fluid interactions with that adsorbed layer. In the case of a protein, that's a little vaguer, but yes, I actually would consider that a structural force.
I have a quick question. Is the structure that is implied after you immerse it and do the spectroscopic study the same as the 2 nanometers or half a nanometer when the electrode's immersed?
Yep. That's a great question. The only thing that we can do to answer that question that we have done is compare spectra that we can get, for example, with surface-enhanced Raman scattering in solution with that we see outside in the residual film, and they are largely the same. Okay, they are largely the same for the systems that we've looked at. It's a hard question to answer, but to the extent that we can do experiments to address it, we think yes. That's with a caveat that there is a second interface that will have an influence on the fluid molecules near the vapor-liquid interface, okay? And so to the extent that alters what is in that residual layer, it may not always be true, but for the systems that we've looked at, it has been more or less true. Okay?
Other questions for Jeanne?
Dick.
Dick?
Jeanne, are you familiar with the technique of capacitive desalination?
No.
You know, I think I'm no expert on this, but I think they do something very similar to this. There's a huge literature on this. You know, they put an electrode into a salt solution, apply a potential, and then just pull it out and pull out ions. We do this over and over to desalinate the solution. And I think it's actually a commercial process, and there may be some relevance to the sorts of things you're doing.
Yeah, I mean, it's another forced dewetting situation there, right? And it's a question of what's coming out. What we know is if we, in these electrolyte solutions, if we rotate out of the solution too quickly, and if we don't have a saturated vapor environment to keep the fluid stable, you crystallize out the salt, which is not the intent. And so if you have a fluid vapor that is that stabilizes the film, that does not happen even at these higher concentrations. And so we don't, you know, I think that what they're taking advantage of in that case is actually the crystallization as the fluid evaporates. We have intentionally stabilized our fluid so that that will not happen.
Thank you, Jeanne. I think we need to move on. Thanks for a great talk.